So as you can see today, I'm out of the class, but I wanted to make sure that we continued learning and didn't lose the opportunity to continue talking about astronomy. So I made this video of what we would have talked about in class, and we would have talked about stars. So here is a short video on stars. First thing we want to talk about is where do stars get their energy from? Here you can see stars get their energy from nuclear fusion that's going on inside the core. This process is taking hydrogen and fusing them together to form a heavier element, helium, and that results in a lot of energy. And that is going on, and all that energy from the sun, the electromagnetic energy that's radiating through space to us, and we'll be talking about that result of when that energy reaches our surface. But anyway, stars, so all stars in the night sky are going through the same process. And stars can be grouped into constellations, which is what we're more familiar with when we look up in the night sky. Maybe not individual stars as much as the constellations. Some of the ones that we're very familiar with are Ursa Minor and Ursa Major. Remember Little Bear, Big Bear. And we should also make sure that we can use the Big Dipper to help us find Polaris, which is that red star in the night sky. To continue talking about stars, stars have different sizes, mass, surface temperatures, and surface temperature also affects the coloring of the stars. And we'll be talking about stars have different brightnesses, or luminosity is what we're going to be using when we're talking about those stars. Luminosity is the total energy output of the star. It's how bright it is, and usually if it's very luminous, it's got a lot of energy that it's emitting. And if it's not very luminous, then it doesn't have a lot of energy to emit. Colors of stars kind of coincide with the temperature, and so we are going to be looking at our reference table here in a second and talking about the different colors. To go over, you have a nice picture here that can help you with stars and colors. Here you can see this side of the chart. We're going to learn that on the right side of the chart, your stars are cooler in color or in temperature and therefore have a red color. Here they are blue in color, and that tells us that they're very hot. So what colors are hot? That's going to be our blue. What colors are cold is your red. And I'm going to be showing you that in your reference table here in a second. So if you would, look at the reference table here. This is the same chart that you have in your reference table on page 15. Just to go over some of the things the chart will tell us. Here we were just talking about luminosity. There it is for you, and it tells you what the definition right underneath there. Rate at which a star emits energy, so that's what it's talking about in relative to our sun. And you can see on this chart that the sun has a luminosity of 1, and everything's relative to the sun. You're either emitting more energy than the sun or less energy than the sun. Here down at the bottom is surface temperature, and here you can see the temperatures in Kelvin, but you can also see the colors down below. You can see blue, white, all the way down to red. And to make sure that you're reading this carefully, remember the 2000 over here, that's your red color. And then over here is your 30,000, that's much hotter, that's your bluer colors. Over here on the other side, here you can see just talking about overall size or how massive the stars are. You can see these are going to be your smaller stars down here and your more massive stars at the top. So to continue talking about stars, we just finished talking about looking at our reference table and looking at some of the axes and what's labeled on our chart when we talk about stars on page 15. But we want to also talk about life cycles of stars. Stars have a beginning and they also have an ending. That depends on the amount of mass that they have when they are being formed. So here, the Hertzsprung-Russell diagram, page 15, will also help plot. Even though it plots the luminosity and surface temperature, it also labels the different stages of a star in its life cycle. So we're going to show you that here in a minute. In that diagram, you have different types of stars. You have what's called red giants that are 10 to 100 times greater than our sun. You have what's called main sequence stars on your reference table that that are actively taking hydrogen and forming helium. They call it the hydrogen burning cycle of the stars. You have supergiants, which are very, very luminous, but still relatively cool in temperature, and white dwarfs. So on this Hertzsprung-Russell diagram, page 15, not only do you have temperature and luminosity, but you have stars put into different groups based on their luminosity and their temperature. So let's take a minute and look at that. So here is the same page 15, but now you can see the different groupings of stars based on those temperatures and luminosity. But you'll also notice underneath them some other words like intermediate stage or early stage, and in this case, late stage. So this diagram also not only puts the stars into groups, but also gives us a clue as to when they are in those groups, what stage are they in their life cycle. So let's, for instance, take something like our sun, who is relatively average size star, and what would its life cycle be? So our sun is a main sequence average size star, and here is a nice picture to show you what's happening here is the nebula, the what we call the area where stars are forming, and here is our sun. It's formed and now is on the main sequence. And so as the sun is taking hydrogen and fusing that into helium, it's eventually going to run out of fuel. It's going to run out of energy. And so what happens to the star when it gets to that part of its life cycle is it's going to eventually expand and become what we call, so this is our main sequence. So I'll write that in there for us. Bad writing, sorry. It will expand out and become a giant. And then eventually all of that extra all this extra material will eject off into space and what will be left is what we have, a white dwarf. So that is our life cycle of a star like our sun, where it begins once the energy starts to, the hydrogen starts to go away, it's going to expand into a red giant here, and then eject all that material out into space, and what will be left is the core of the star, and it will then be called a white dwarf. Now, what if you're something that is more massive than our star? Well, this is a lot different kind of scenario where you already are a giant or supergiant. What's going to happen is the fusion is going to continue, but eventually that hydrogen is gone and the helium start to fuse together to make heavier elements. And once that starts to happen, these massive stars become very unstable. And as a result, they will actually go through the supernova stage, which is a star exploding. And two endings to a supernova is either one, a neutron star, or over here, a black hole. And here you can see a star with a mass 8 or more times greater than the sun will become a black hole, a neutron star. And here is a nice picture. Here's the nebula of where the star is forming, very massive. Eventually becomes a supergiant, explodes supernova into either a neutron star or a black hole. And here's just another image of putting both of what you saw, those two pictures into one. The nebula with mass being the determiner of what path the star will take on its life cycle. If it's something like our sun, into a red giant, planetary nebula, and white dwarf here, protostar type, the beginnings of early parts, very massive, will become a red supergiant, exploding into either a black hole or a neutron star. So I'd like to end the video with reviewing our reference table again, but then trying to show you some of the other questions that you could possibly be asked when it comes to this. So here we could ask you about, of course I could ask you about temperature, of different stars, individual stars like our sun, or maybe I might ask you about a star like Polaris. If I asked you the temperature of Polaris, you would say 6,000. If I asked you the color, you would say yellow. If you further down here, you can see yellow. I might ask you, is the Polaris more or less luminous than our sun? You would say more luminous because here's the sun and we can see that's much higher. Or I might ask you to compare Polaris to another star like, let's say, Barnard's star. So here we have Polaris and Barnard's star. I might ask you, is Barnard's star hotter or cooler than Polaris? Is it more or less luminous? And so in this case, Barnard's star is cooler and less luminous. Okay, so those kinds of questions could be asked. Don't forget you have your different main sequence stars, your different supergiants, that the different groupings based on where they are in their life cycle. And also, don't forget this is often forgot when you're talking about how massive those stars are. So here's your reference table, page 15. I would like you to stop the video and go to the ticket out and see if you can answer some of the questions that are going to just test your ability on being able to pull information off the chart here.